Hi, Chris.
Hi, Bob.
How you doing?
I'm doing well, thanks.
Good. Let me introduce us. I am Robert Wright. This is the Wright Show. You are Chris Impey, and you are in sunny Arizona, or at least usually sunny Arizona. You're at the University of Arizona, where you are University Distinguished Professor in the Department of Astronomy. You have a ton of academic publications. At least 170, I gather. And in addition, you've written a couple of introductory textbooks, a novel, and some popular science books, including How It Ends, published in 2010, and How It Began, ironically published in 2012,
Yeah.
after it ended, and Dreams of Other Worlds. And this book, which we're going to in particular focus on today, Humble Before the Void, a Western astronomer, his journey east, and a remarkable encounter between Western science and Tibetan Buddhism. It's a very interesting book, and I think will afford us the opportunity for a very interesting conversation. Because first of all, the encounter with Buddhism is interesting, and the question of whether there are parallels between kind of modern physics and Buddhist philosophy, or in some cases tensions between them, which, in the book leads to the broader question of the interface between physics and philosophy generally, a number of philosophical questions that get raised, which in turn leads to a subject of great fascination to me, which is just how weird physics is, and in some cases hard to fathom. So I want to talk about these, cover a little of all of these things. First of all, why don't you tell us how you wound up in the Himalayas talking to a bunch of Tibetan monks in exile. You were not in Tibet, I gather, but you were in the Himalayas.
No, I've never been to Tibet, unfortunately. Yes, I got a call pretty much out of the blue from a guy called Bryce Johnson, he was an environmental science PhD out of Berkeley, and he got looped into the helping the Tibetan Library organize science programs for monks there, and so he saw my name in circles of teaching and summer schools and so on. I do a fair amount of teaching beyond my university. And he just said, how'd you like to go to, northern India to teach Buddhist monks cosmology? And, it's not a question you ruminate over. You just say yes and figure out how it's going to work. So the first trip was Dharamsala. I've been 6 times since, and it's fun for a number of reasons, but also we move around the country. There are about 20,000 monks, Tibetan Buddhist monks living in India. About half of them are in the north near Dharamsala, the government in exile, and the other half are in huge monasteries down south. So I've sort of moved around the country doing this program.
Mm-hmm. So what was your mission exactly?
So the goal, stemming from His Holiness's desire that's now 15 years old to inject science and math into the monastic curriculum.
His Holiness being the Dalai Lama, who wrote the foreword to this book.
Right, and he's been a very activist about, really in larger terms, about not having the Tibetan culture become a museum piece, given that they have no homeland. And part of that rejuvenation of the culture is to make it modern, and the monastic tradition is venerable, of course. It's the strains of Hindu and Buddhist philosophy, going back thousands of years. And it's very rigorous. The monks are trained extremely well, but they don't have a lot of technical training, math or science. Their typical math level is 8th grade, I would say, in an American equivalent. And so out of his own intense interest in science, the Dalai Lama has been dialoguing with Western scientists for 3 decades. He, has moved towards injecting science into the monastic tradition. And in the first instance, that's by importing Western teachers like me to teach workshops, sequential workshops, and have cohorts of 30 to 35 monks and nuns go through a pretty rigorous series of 3-week programs over a few years. Obviously, in the long term, that model is not going to do the job with tens of thousands of monks and nuns. So the goal is to have the best of the products of these workshops start to be teachers themselves, and set up science centers in the major monasteries. And that's now starting to happen.
Mm-hmm. Okay. So you were their science teacher. and you covered some basics in physics. And I want to just start maybe by reviewing some of the basics in physics, well, for my benefit, for the benefit of our viewers and listeners, and because it leads to the weirdness of physics right away. So you're talking in the book about Einstein's accomplishment and the fact that, you know, in his famous equation, E equals mc squared, he brings together these two things, mass and energy, and shows that they are convertible into one another in principle. Or another way of putting it is that it's matter and radiation, right? And that's the way you describe the book. And you say that they would seem to be very different. They are in many ways different. Matter has heft and substance and resists changes to its motion, you write. Mm-hmm. Radiation is intangible and evanescent and fleet-footed. So I guess that's true. A question arose for me, doesn't light, which is a form of radiation, resist some changes to its motion when it like bounces off a mirror or something?
Right. Well, it has it has the equivalent properties of a particle. So going back to Einstein, the notion of wave-particle duality, the fact that you have to think of light both as a wave and a particle. He won, of course, the Nobel Prize for the photoelectric effect, which is the demonstration that light has particle properties. Its wave properties were known 100 years before by interference and diffraction and those various wave-like phenomena. So both truths hold, and Einstein was just able, in a physical theory, to sort of reconcile those two aspects of light.
So you mean when it's bouncing off a mirror is when it's acting like a particle?
Yeah, when it's conveying momentum, conserving energy. And then when it's hitting the edge of a mirror and kind of bending slightly around the mirror, that's a wave-like property, the sort of diffraction. Mm-hmm.
There's something that's always puzzled me, and it's kind of hard to articulate what the puzzlement is, which is just, it seems fascinating that light, which is so fundamental to human life at least, and to a whole bunch of life. I mean, in the sense that it's kind of in a sense our most important means of perception. Mm-hmm. So it's that. It already has this special relationship to us. And then it turns out to be implicated in this relationship between energy and mass in the sense that a direct derivative of it is the constant of conversion, right? I mean, you can imagine, it seems to be a universe in which the equation is E equals 3.5 m, right? In which the constant of conversion is just a number that has no other significance, right? You can imagine that, and yet it turns out that light is just mathematically the source of the constant that connects mass and energy and governs their transformation into one another. And I'm just wondering, is it totally understood why that is the case? I mean, do true physicists that's not a puzzle to them because they understand why that would be?
Well, in the world of physics, it's a little bit arbitrary. So in the world of theoretical physics, the speed of light is, the number is, of course, a function of our unit system of, meters, kilograms, and seconds. That's a choice we make to have metric units defined that way. When physicists actually do their work, they set up unit systems where c equals 1, the speed of light is 1, and Planck constant equals 1. You can actually redefine units to just normalize out those constants. It is arbitrary in that sense. The only thing that's meaningful about it is that it's when you take reasonable physical units for mass and energy, their interconversion involves a large number. And that's the statement that if mass represents frozen energy, it represents an awful lot of frozen energy. And that's the efficiency of nuclear power and so on, where it's millions of times more efficient than, say, chemical energy, which is just rearranging electrons in atoms.
So wait, are you saying that at a certain level of kind of abstraction in theory, you can just substitute 1 as the constant, but in the real world, where we actually see how much mass is equivalent to how much energy, you actually have to use a huge number that turns out to be the square of the speed of light? Or
right, that's just a function of the definition of the units, but the physical fact that frozen mass, if you want to think of mass as frozen energy, which is a metaphor, but it's not an inappropriate metaphor. It's a huge amount of frozen energy, and liberating that energy through technology, through a fusion or fission reaction, tells you that it's the equivalence involves this very large conversion factor,
which happens to be the square of the speed of light.
Yeah.
Does my puzzlement seem like I'm missing something?
No, but so there's two pieces to it. The arbitrariness of the speed of light in any set of units, which you have free choice in how you define your physical units. You don't have to use kilograms, or you don't have to use seconds. Because in a sense, a second is defined as a number of oscillations of a cesium atom. So that's another arbitrary thing. To physicists, the normalization of units is completely arbitrary. And therefore, the speed of light as 3 × 10⁸ meters per second is completely arbitrary. It's a function of our choice of unit systems.
Okay. I'll have to ponder this exchange and see how close to enlightenment it brings me as I reflect on it. Meanwhile, on to another strange thing about light. As I understand it, if if there's a train passing by me and I'm measuring its velocity, I'm standing still, and then I start running in the same direction the train is moving and measure its velocity, I get a different number, right? Because relative to me, the velocity changes when I start running. Now, I think I've heard that with photons, with light, that's not true. So if I start running in the direction of the light, its speed, the speed of the moving photons relative to me is exactly the same it was when I was standing still. Is that right?
Right. So this is the difference between Galilean relativity and Einsteinian relativity. So in the world of physics, from the time of Galileo through to the time of Einstein, so including Newton, of course, velocities just add and subtract in an appropriate way, a vector way, based on the relative motion. So if you're moving towards or away from something, you just add or subtract in the way you would expect. And that's standard ballistics, standard Newtonian mechanics, standard Galilean relativity. What Einstein had to do was, he was, a brilliant theorist, but he was very deeply motivated by the physical world as we measure it. And as he approached the idea of light, he was aware of this very foundational experiment in physics, the Michelson-Morley experiment from 1895, which had used the premise that, well, the Earth is moving, the Earth is spinning and going around the sun and is moving relative to the stars and so on. So with all these relative motions, we should see the adding and subtracting of our motion in space from the light speed of things that are out there in space, in the sense of if you ran towards a beam of light or ran away from a beam of light, it should be the speed of light plus or minus the speed you're running. Mm-hmm. And this is just now mapped into the celestial realm where you can do the experiment, and the speeds are large, so it makes a nice experiment. And the Michelson-Morley experiment, just measuring within a lab the arrival speed and timing of light at different parts of the Earth's orbit, found nothing, found no effect, and they should have been able to measure it. If the speeds had added and subtracted in that sort of traditional way, they should have seen a significant effect. It was a subtle effect, but they could detect it. So the Michelson-Morley experiment was a null result and essentially said that regardless of your particular motion of the human or the planet or our position in space relative to light emitters, the speed of light always is measured to be this same number. So that null result was the inspiration for relativity, because Einstein took that experiment as the way the world works, and then he had to puzzle over how that could be. And that, that's the brilliance of relativity, that, he was motivated by experiment, and the consequence, the implication of this really weird result that the speed of light doesn't seem to depend or vary with the motion of the observer, implies that since the speed is a distance divided by a time, then if the ratio of those two is always constant, always a fixed number, both the numerator and the denominator must be supple, must be variable depending on your motion, and that leads to dilation of time or stretching of time, and it leads to compression of lengths, which is the Lorentz contraction, part of relativity. So these things flow logically from an observational result of 1895, and Einstein built his theory around essentially the premise, the postulate, that the speed of light is constant and doesn't depend on the motion of the observer, which is what's observed.
Mm-hmm. So, to somebody who thoroughly understands the theory of relativity, it ceases to seem so mysterious that the relative velocity of light wouldn't change as you move.
Yeah, and he was also, Einstein was motivated by classic electromagnetic theory. In fact, the kind of whimsical question that set him off on the road to relativity was in the anecdote. I think it's a true anecdote. It's appeared in all his biographies. Was he was 17 years old, and he had a friend, Marcel Grossman, a fellow physics student, and they were living in Switzerland, and they were on the banks of a river just goofing off, and Einstein just said, what would the world look like if I rode on a beam of light? Because that's the fastest thing there is. What would I see? And that simple, whimsical question of a teenager, impelled him physically to work out what could be going on. And in electromagnetic theory and Maxwell's theory from, a few decades before, the speed of light is a constant. The electromagnetic radiation all travels with this particular speed, and that number doesn't change according to the situation. So although Maxwell's equations are not relativity, they contain the seed of this issue, because this is this universal constant that seems to be built into Maxwell's equations. He didn't, follow the logic that Einstein did, but he could have actually. It just they didn't have the experiment, the Michelson-Morley experiment, to sort of put it in your face that light is always the same speed regardless of motion. Mm-hmm.
So what led him, Einstein, on the path of discovery is this idea that, well, suppose you're riding on a flashlight beam or something, but in the end, is it fair to say that that relativity also is partly, he's kind of saying, imagine the view from nowhere, in the sense that, we're used to viewing everything from our perspective, but what if you had to make sense of these things like velocity and so on, and you have to imagine yourself being like nowhere in particular in the universe? It is kind of the view from nowhere that also leads to relativity, right?
That's right. And the other, to the physicists of the turn of the century, what the Michelson-Morley experiment was actually testing was whether there's something called an ether. So there was a hypothesis in physics, back in the 19th century, that the reference frame for motion must be this sort of invisible fluid, that fills space, and that's what you measure yourself moving with respect to. The Michelson-Morley experiment said essentially there is no ether, there's no fluid, there's no reference frame, because and relativity is that. Everything is relative, there's no absolute reference frame, and that was an implication of Einstein's theory. And so, in a sense, everywhere and nowhere, they're all the same.
Right. That's interesting. And you might imagine that once you dispense with the notion of the ether, you could still say, okay, but still, in some abstract sense, there's like a grid. There's like a three-dimensional thing, and it makes sense to think of that being there. In some sense, that is governing reality. But Einstein was saying, wrong again. You shouldn't think that way.
He was, to his credit, he was very driven by experiment. I mean, he talked to physicists about what was measured, and his theories were always motivated by observation. And they said, we don't detect an ether. We have no way of defining a reference frame out in space, and so there is no reference frame. Now, that gets modified slightly with expanding universe and Big Bang cosmology, because in Einstein's in general relativity, which comes a decade afterwards, he's now talking about space-time as an entity that is a dynamic entity that in our universe is expanding, basically. So it's a mathematical construct that grows with cosmic time as the universe grows.
Okay, you mentioned the dilation of time, which you mentioned in the Earl of Light or something. Anyway, we'll get to what you mentioned in the book, this whole set of considerations that leads to the possibility of, in a certain sense, time travel, slowing down your rate of aging if you're moving fast enough. Before we get to that, just one thing on this idea that light's speed relative to me doesn't depend on whether I'm moving. It seems to me, in general, the idea with the wave-particle duality is that Okay, maybe it doesn't make sense to us that something could be kind of both a wave and a particle, but at least in any given situation, if you think of it as either a wave or a particle, it will make intuitive sense. There's some situations in which the way to make sense of it is particle. Some situations you call it a wave and it all makes sense. It seems to me in this case, it makes sense to think of it as a particle, right? Because you're talking about velocity, but it still doesn't make sense. I mean, it doesn't make intuitive sense to someone who does, right? I mean, with the standard quantum physics experiments, I can know like virtually nothing. And if they say, well, just think of it as a particle, I'll go, okay, it makes sense. But with this, it still doesn't make sense.
Well, because the third piece of the relativity concept is that you have the Lorentz contraction, so you have this compression of a linear distance in the direction of motion as it approaches the speed of light. That's just the standard equation of special relativity. You have an analogous dilation of time or stretching of time in the reference frame of the traveling entity as you approach the speed of light. And then the third piece is the mass, is the increase in mass as something that you're choosing to call a particle rather than a wave, approaches the speed of light. As you choose to accelerate a dynamic entity, a particle, an object, a baseball, whatever, towards the speed of light, its mass grows as it approaches the speed of light with exactly the same factor, mathematical factor, that time stretches and that length contracts. So the formalism is completely equivalent for those three situations. And so that's the particle way of thinking about it, that as as particles move faster and faster, their mass, and therefore in Newton's sense, their inertia, their resistance to a change of motion increases. And that, of course, becomes part of the reason why light is the fastest thing there is, why no other entity in nature that we know of can move at light speed or faster.
Mm-hmm. Okay. Which leads to time travel. I mean, ultimately, this idea of dilation, contraction, whatever, and we've all seen the movies, right? Planet of the Apes, Interstellar, mm-hmm. and we think that's actually true, right? I mean, I don't know if we'll ever get to a point where we can move fast enough, close enough to the speed of light for this to happen, but in theory, it's actually true. You could leave the planet, come back, and 3,000 years have passed.
Right. It's called the twin paradox, and in physics, it's not really a paradox in a sense that, yes, if you can manage sort of relativistic or good fraction of light speed travel to a destination and then return, your clock relative to the people you left behind will have slowed down by the relativity equations, and therefore you will be, biologically, younger than you would have been if you'd stayed on Earth. Mm-hmm. I mean, it's an experiment we can't do, but in principle, that's what the theory says.
And what that suggests is you could move forward in time. You could leap forward. It's less clear, I gather, that you could move backward in time.
Well, yes and no. I mean, it does not say anything about causality, so there's no violation of causality here. It's just different clocks, So with different relative motions, clocks will run at different rates. You can't, again, violate cause and effect by that mechanism. You're just talking about different rates of forward motion of time, so there's no reverse time implied by any of that.
Right, but I mean, it seems like more paradoxes arise also if you're moving backward in time, right? It's like, if I'm moving forward in time, and then you go there and you go, whoa, this is the way the world would exist in 3,000 years if I had projected myself into it and influenced things. But the fact is I did. So that's just, in a way, straightforward causality. Whereas if I have the option of going backward, the grandfather paradox, I kill my grandfather, whatever.
Right, but the catch, of course, is that in this idea, the twin paradox, the space travel twin paradox, you're traveling to a remote location, so you're not time warping at your current location, which might let you violate causality and kill your grandfather and all that stuff. You're doing it at a remote location, so you can't get to both. You can't have it both ways.
But I can come back to planet Earth. I can come back to the same place centuries hence.
But you're not right. But you're not. You're coming back centuries hence. You're just coming back less biological time for you, hence, than has been experienced by all your relatives and friends and family.
Okay.
Stay here.
Okay, so I want to get into some areas where you make particularly explicit connections with physics and Buddhist philosophy. I also want to say this book is a lot more than that. I mean, there's a lot of interesting stuff about just interacting with this culture, the culture of the Buddhist monks. There's a number of really beautiful pictures. So it's, you know, to some extent kind of anthropological. But as for the philosophy, one thing you get into is this Buddhist notion, sometimes called, well, typically called emptiness is the typical translation of the term. And you want to talk about a connection you saw between physics and emptiness in the Buddhism?
I mean, I guess these can be you know, they can be misapplied. I was trying to be careful not to overemphasize false parallels between science and Buddhism, but obviously in science now, the vacuum is a very rich concept. You know, there's no such thing as nothing in physics or in cosmology. The vacuum of space, you know, out there between galaxies, as close to a total vacuum as you can get, is a place where, you know, space-time is expanding and dark energy exists, and that's an entity that we can measure. The physics of a laboratory vacuum involves the creation of energy of particles and antiparticles, and that's a real phenomenon that you can measure and you can benefit from. You can do experiments based on that. So, and then in theoretical physics, the vacuum is just this very rich concept for exploration. So, you know, nothing in physics is as far from boring as you could get. And in Buddhism, you know, emptiness is a much more different spiritual, almost psychological concept. In a sense, almost a tool towards trying to see nature and your place in it in a more reasonable way, in a more sensible way. But the monks, we talked about the physics of it. I mean, I'm not trying to explore just their view of their spiritual path. I'm also interested in how they think about nature, how they think about space and time. And as much as they would articulate it before having been taught the sort of modern scientific view, it was very similar, you know, that the emptiness of space, or the place where the many worlds exist in their philosophy, is a rich place of potential for life forms, of sentience, of many worlds, of all of the things that, you know, science acknowledges are going to be out there in space too.
So the basic kind of physical fact is that almost all of space is in some sense empty, mm-hmm. right? The kind of physical stuff, as we define that, is they're few and far between.
Right.
And when they heard that, the monks, they found that as resonant with the idea of emptiness.
Yeah, because they recognize that, you know, the things that are familiar to them, such as, you know, the earth, consciousness, the existence of sentient beings, you know, comes from a construct of an original and eventual nothing, you know. So there's creation, destruction, there's cycles of time, and it's completely reasonable to them that, you know, something can emerge from nothing, and that something can be very rich.
Yeah, I want to get back to the something nothing business. I think you're right that emptiness, I mean, it's tricky because, well, first of all, as with all philosophies, there are schools of thought and different ways to think of it. So there's kind of mind-only Buddhism, according to which, you know, consciousness is all that exists and the rest is completely an illusion. And then there are less extreme forms philosophically. And then there's the fact that, as you suggest, this is also a kind of experiential doctrine, in the sense that meditators may say, I sensed the emptiness, you know, as part of a meditative experience. So you've got this kind of psychological apprehension, and then a philosophical, you know, articulation of it. And there's variation in both of those, the way people describe the experience and in the kind of philosophical articulation.
Right. And we were talking about both of these, of course, you know, in a humorous way. We would talk about, you know, the monkey mind, that sort of the, you know, that kind of frenetic thing that's always going on in most people's heads, that, you know, where at least trying to empty your mind is an extremely challenging thing for anyone to do, Western or Eastern, whatever their tradition. But in their tradition, a very important and purposeful thing to try and do. The physical meanings of emptiness were a little different, were a little harder to pin down, actually, because as you mentioned, there are, just as I encountered dozens of cosmologies in the Buddhist tradition, and the Dalai Lama's, kind of humorous about this. He just says, oh, most of those are just silly. He looks at the traditions of Buddhist cosmology and acknowledges some of them as antediluvian or obsolete or old-fashioned thinking. And there are many ideas of emptiness, too, in the philosophical tradition, and I probably only encountered a few of them. Mm-hmm. It was usually the geshes, the more senior monks, whose English was better, where I could just have a real deep conversation about that.
Mm-hmm. One way of that emptiness is sometimes articulated is to connect it to a concept that you refer to in the book, dependent origination, kind of the idea that everything is independent. There's nothing you see in the world that could actually exist without physical interaction with its surroundings. The best example are like trees and things, which need nutrients, but the claim is that you can also view all of physical things that way. So in that sense, the distinct form you attribute to things like lamps and so on is in a way imaginary, because the boundaries are in some sense misleading. So there's that, that's kind of a less extreme way of thinking of it than the mind-only way. But that, in your book, you mentioned this idea of dependent origination, and you see, I think, some resonances with physics there that aren't, I don't think, just about the idea that so much of reality is a vacuum, right? Or
No, they're part of the long tradition of Western philosophy. So, the Platonic idea that there's a world out there independent of our knowledge of it or our way of viewing it has sort of been replaced in physics with a physical view where, the act of observation affects the outcome. That's a truth of quantum reality, and that since the world is just composed of a large number of particles at that root level of physical reality, there's clearly a relationship between, the act of observation or the data you can acquire from the physical world and what you infer about that physical world. So it's become inappropriate in physics to sort of talk about underlying reality. That was, of course, the trap that Einstein, had trouble evading in the last part of his life. He was very unhappy with quantum physics as it was formulated in the 20s and 30s, despite its enormous success, to the present day, it's an enormous success. And so he was a Platonist in, really hoping and believing that there were underlying theories that we just hadn't approached yet. There was an underlying reality that we could describe, that quantum physics was not the final theory of nature. And, to his death, he was not proven right on that. And in fact, since then, the things that he found most abhorrent about quantum theory have been shown to be true. Then physics is non-local. Get over it. That's a reality of Bell's theorem in the last 30 years of quantum physics that he would have found extremely unpleasant. But it again says that the Platonic view seems to be inappropriate.
Yeah, well, it is super weird. The Bell's theorem, this idea of entanglement, this idea that when I measure something here, then kind of instantaneously, as I understand it, that can influence the state that a particle far, far away will occupy if you measure it, right? That's instantaneous influence in a certain. It's not, in a way, it's not information moving faster than the speed of light, because you can't use it to send a code or anything. You can't encrypt any information and send it that way. But that's super weird, right? Do you have trouble grasping that kind of non-locality?
Sure. Philosophically, I have trouble the way a lot of people do. I can read the math of it and the equations and the physics of it, and the experiments are pretty clear. Actually, this field has moved quite a lot in the last decade, and literally within the last year, there are three small loopholes in Bell's theorem, in the fact of physics being non-local, that have been closed just in the last year. There's only one tiny little loophole left. It's like, it is what it is, that the experiments have spoken, they're all consistent. People have now demonstrated non-local physics on transcontinental scales, not just in a lab over meter scales. As you said, it's not a way of violating causality, because if you form entangled quantum states and want to transmit information to that remote location by coding quantum states and sending a key, you do it at the speed of light. So it's not violation of causality.
Well,
but the non-locality of the physical situation, the coupling, the remote coupling, an apparently instantaneous coupling of physical states appears to be real. It's what we measure in the lab. It's what we measure.
But it does seem to be, it's in a certain sense, as we said, instantaneous influence, which sounds kind of causal, you know.
Right. It's a substrate reality that's non-local. Physics is non-local. But if you want to operationalize that to send information, you're
Right.
subject to some constraints, and those in the end amount to light speed, travel, causality applies, and so on.
That is true. I mean, it's funny, I gather Einstein said, look, quantum physics couldn't be right, because if it were right, then you would do this experiment about entanglement, and it would turn out there was entanglement, and that's crazy, that there could be instantaneous influence, right? It was a reductio ad absurdum from him, and then they actually did the experiment, and reality was that weird, right?
Oh yeah, he'll be spinning in his grave faster and faster as these experiments continue.
And related to all this is another thing he had trouble with, I think. I mean, he believed, I mean, in quantum physics, things happen for truly random reasons. There's a fluctuation. There would be no way, even in principle, of predicting which way, whether it's going to be heads or tails, so to speak. And what that means is things happen that have no cause in the physical universe. He could not accept that. He insisted we would ultimately discover so-called hidden variables that explain these things. And I guess that's connected to entanglement, right? Because, well, go ahead. What were you going to say?
Right. Hidden variable theory would be, a substrate theory that within which entanglement would be an emergent property, something that you could describe based on these hidden variables. I guess the only viable line of philosophical and physical reasoning that still is in play is what David Bohm spent most of his late part of his career as a physicist working on, and it is a kind of hidden it's a sort of the best expression out of physics of hidden variable theory, the kind of thing that Einstein was looking for. And I don't talk to physicists all the time about that kind of stuff, but the best philosophically inclined physicists that I talk to say, Bohmian theory still has some, meat to it, still has some substance. It's a reasonably motivated physical theory. So that's Einstein's agenda, as it still exists, being played out just by a handful of physicists now.
And is that related to there being one small loophole left in Bell's theorem?
No, it isn't actually. The small loopholes that have been closed and one left are just pure technical things about how you design the experiment. Was there a little escape hatch in the way you designed the experiment? It's about experimental design.
And
really.
The final loophole is closable in principle. They could do the experiment and they will.
There's 3 or 4. I mean, this is a niche in physics. It's a very important niche, but the people doing these experiments are gonna just they're gonna demonstrate beyond any doubt that physics is non-local with no loopholes. It's going to happen soon.
So you mentioned this question of why there's something rather than nothing, and you do get into that in the book that attempts to kind of wrestle with that. And so I have a couple of questions. It's not necessarily the same question as why the Big Bang happened, I think, but you do talk about that, and they would seem to be related questions. And one thing you say is in the early, that one theory about why the Big Bang happened is in the very early universe, this is a quote from the book, the Big Bang started due to a quantum fluctuation, the smallest jolt, so to speak, at a subatomic level. Now, for there to be a fluctuation or a jolt, there has to be something to fluctuate or something to get jolted, right?
Right. Well, yes and no, in the sense that we're back to the richness of the vacuum. So out of a physical situation where there is, nothing, as far as a physicist would define it, it's pure vacuum, then the second version of Heisenberg's uncertainty principle, this is the sort of simplest way to think about it, is the the uncertainty in energy times the uncertainty in time is the Planck constant, just as uncertainty in mass and momentum as the product of those is the Planck constant. So that tiny indeterminacy in physics applies to energy and time as well as to mass and velocity. And so you play with those variables, and you can see that if for a short enough period of time you can borrow a vast amount of energy from the pure vacuum, i.e. create a pure amount of energy. And of course we see that in the spontaneous formation of particles and antiparticles that come in and out of the vacuum and then evanescently and then disappear. So if you just amp that up enormously, but the same principle, you can borrow the energy to create a universe and give it the impulse to be expanding space-time and fill it with radiation that then turns into matter. Matter and antimatter with a slight asymmetry leaves you some matter left over, because we're in a universe with about 1 billion photons for every particle. And so, in a very simple concept, that same indeterminacy can spawn a universe, a very rich and big and old and universe full of matter and radiation.
Mm-hmm. Now, philosophers who want to argue that this scenario doesn't explain why there's something rather than nothing would say, and have said, a couple of things. One is that even a vacuum state is a physical state. Right. You can imagine a universe in a certain sense that doesn't have vacuum states, right? That would be nothing. Right. And the other thing is that you would presumably, even with a vacuum state, if you're explaining how something emerges from it, you're positing laws that govern that transformation, and you can imagine a universe without laws. Laws are something, right? So it's in that sense that this scenario is said not to answer the truly philosophical question.
I agree. No, it has not answered the philosophical question, because you're still left with original cause of those vacuum states. You're still left actually with much bigger problems of no real physical theory that describes what the ensemble of vacuum states might be from which one fluctuation would give you this universe, because the corollary, of course, of the quantum fluctuation origination of the universe is the multiverse theory, where there are other possible space-times and other situations. They're sort of atemporal. We can't really talk about them with a particular time sense, but they're contemporaneous, if you like, loosely defined. And there's no physical theory for how that works. So, the physics of this is really not developed or understood at all. And it's a sort of cop-out to just talk about a multiverse, or to make an anthropic argument that this universe has particular properties that are conducive to life, thereby explaining coincidences in physics that you otherwise are mysterious, because we don't have that substrate theory. And it's not really coming with any speed from string theory or any of these frontier theories of the physical nature of matter. Mm-hmm. So I would say, the physicists have set themselves an agenda that's extremely challenging, and they have not answered these philosophical issues.
So a very short drive from where you are at the University of Arizona is Arizona State, where Lawrence Krauss teaches, and he wrote a book called The Universe from Nothing. I think the subtitle was Why There's Something Rather Than Nothing. So it sounds... And I think he was making an argument somewhat in the spirit of what we've been discussing. Yeah. So it sounds like you're unpersuaded that...
Yeah, I mean, there's optimism. I applaud the optimism of the theoretical physics community that they can answer, say, the question of why there was a Big Bang. But, I'm an observational cosmologist, so I use telescopes and I'm rooted in data, and I'm a little skeptical of, I acknowledge metaphysics is a very important and powerful part of science. It's a sort of base level of science, but I think we're in the realm of metaphysics and still talking about origination of the Big Bang or precursor states or anything like that. There is no physical theory that can be tested. That's the simple way of putting it as an observational scientist. And to some people, there are some pretty strong pushback, as there is pushback on string theory for not being testable and not being part of the edifice of science, that these pre-Big Bang notions, the multiverse idea, whatever you want to say, are not formal science yet. They're metaphysics.
Well, and also, if there were a theory, if it were a testable theory, it would presumably assume the form of positing laws that transform one physical state into another. And if that's what's going on, you aren't back to nothing yet. You're still starting with something. I mean,
it's a rich vein for exploring, but I'm a little skeptical. So, and Brian Greene's another good example. I mean, he will in his books, he breathlessly and euphorically describes these approaches to possibly understanding the fundamental nature of matter and therefore also potentially these precursor states to the Big Bang. But the truth is, we are so far from anything that approaches a physical theory.
Yeah. I talked to Lawrence Krauss about this, and I asked him, and at one point he said something that I wish I had followed up on. He said, no, really, physics shows that things can arise spontaneously. And I should have said, but wait a second. Spontaneously, in common usage, means you don't know why it happened. Right? I mean, that's, and if you mean that, then we don't understand why something. And if you mean anything else, I think you have to mean that you're talking about laws that transform something into. I guess my question for you is spontaneous like a technical term in physics that means one of those things?
Well, to take it in an area where it's in the lab, then yeah, if you want to call spontaneous matter, antimatter creation, the virtual pairs, which is the Casimir effect. I mean, these are lab experiments that can demonstrate there are spontaneous, if you want to use that word, creations of matter and antimatter from the vacuum, or sort of energy from nothing for a particular period of time, still within the realm of well-understood quantum physics. So yeah, that does happen. I mean, that's an appropriate description of physics of the lab. But it's not mapping that to the realm of the universe, and the Big Bang requires a physical theory that we simply don't have, because these are regimes that are not testable in the lab. They're not part of the standard model of physics. So, you're in uncharted territory here.
And even in the lab, they're thought to be, laws that lead to the so-called spontaneous emergence.
Yeah,
so you're not back to a universe with...
You're still in the realm of well-traveled quantum theory.
Yeah. So the anthropic principle, which you, I think, alluded to a few minutes ago, let me summarize the idea as I understand it, and you do talk about it in the book, and then why don't you give me your views on it. It begins with the observation that if some of the fundamental constants of the universe had been even slightly different, then the universe might not have been hospitable to life. Right. And so you could view this as an argument, it's sometimes viewed as an argument for kind of design, even to the point of saying, well, there must be a God. I mean, this universe was created for life, and and look, we are the life. It led to us, and so that's evidence of design. And then there are various other ways of explaining why the universe would seem to be tailor-made for life. And anyway, you play around with this for a while. How do you come out on the?
I'm not in the camp of the anthropic principle as something that is, let's say, something that is productive scientifically at this point. I mean, I drop back to Bertrand Russell, who wrote about this succinctly and elegantly. Of course, he won his Nobel Prize in literature, so he knew how to write and he knew how to make an argument. And he really slammed the argument for design. You're not allowed to look at features of the physical world or the natural world of the universe that seem to be, tailored around your existence or tuned around the fact that you exist, and you're not really allowed even to be surprised about that, and you're certainly not allowed to weave a whole theory based on that, i.e. an ensemble multiverse of which this universe is one that has very particular properties conducive to stable atoms or biology or whatever. So that at that level, I'm a skeptic about the anthropic principle. Now, the issue of fine-tuning in physics is slightly distinct, and that is, to me, something legitimate. I mean, it's legitimate to ask, why is the electron 2,000 times less massive than the proton, or why are there three families of fundamental particles, and why do things have the masses and the properties they do, some of which relate to the stability of atoms and other things that could tie into our existence. Those are fair questions to ask, and the answers so far are just that we know very well that we don't have a complete theory of physics. We have a standard model of particle physics that's known to be incomplete in several ways, despite the Higgs detection. That's just sort of a missing piece of the standard model, but the deficiencies of the standard model are very obvious. So that just means physics. There's more work for physics to do. It doesn't mean you should jump to some logical conclusion that that's an anthropic in nature. So I'm not really a fan of the anthropic principle, and I also think it's a slightly sterile type of argument because, again, to be part of the edifice of science, it should make testable and unique predictions that can be, that we can test. And I haven't seen any case yet, and certainly in cosmology, where you can do that.
So was Bertrand Russell making the argument that you sometimes hear about the anthropic principle, that it's tautological? In other words, like, obviously, if you're here thinking about universes conducive to life, if intelligent life exists, it has to be in a universe in some sense hospitable to life. You couldn't look around and go, wow, the fundamental constants preclude the existence of life, because you're here. So one argument against this is that it's tautological. Was he explicitly making that argument?
Yes, he was referring to that and the self-selection idea. Someone who's written about this more recently and very nicely is Nick Bostrom, a physicist or philosopher rather, Swedish born, out of Oxford now. He has his own institute. He's the guy who's done a lot of work on the simulation hypothesis, and so he plays with some of these, kind of out there, talking about mind only a half an hour ago, and that Bostrom has played out as a philosopher the sort of simulation mind only idea. But he's also very neatly, as a philosopher, critiqued this sort of self-selection idea and basically attacked a sort of standard. Certainly this strong anthropic principle. The weak anthropic principle is, in a sense, the strong anthropic principle, I think, can be rebutted logically. The weak anthropic principle is just an observation, in a sense, that there's fine-tuning in physics, say, or there are things that we haven't yet explained as part of our theories, but you can't draw an appropriately strong conclusion from the weak anthropic principle.
It's just the observation of the fact of the fine-tuning period. That's the weak.
An unsurprising observation.
Okay. So we're running out of time, but I did want to let you talk a little about as I said, the book is partly, largely a narrative about your encounter with this very different culture. Why don't you talk a little about some of the things you found and what you took away from it?
Yeah, so I mean, it's a singular experience. I was there last October, going back this October actually, so pretty much an annual part of my calendar, and I hope to continue. I just took a job as Associate Dean in Science here, which I hope will not squeeze out this kind of trip. So the several areas where it's always been striking are, first, the fact that as a teacher, as a teacher for 30 years of all sorts of students and big online classes and 18-year-old American kids, millennials, the monks are incredible students. I mean, they're, again, technically naive, as mentioned. Their math and physics background approaching this material is pretty weak, but their extraordinary habits of mind, the kind of habits of mind that we tend to bemoan in the West of our highly distracted and slightly hip, savvy, cynical students, they just don't have it all. They're naive in the most wonderful way possible. They're intensely curious. They're fearless in approaching ideas, and also selfless in throwing themselves into learning, despite the potential for embarrassment or saying they don't know anything. They're sort of like the Uber student for me, and that's endlessly refreshing. So that's a sustaining part of the experience, and I'm still amazed by the things we get up to in the classroom. So that's one thing. Another thing that I guess I alluded to in the book a little bit is that in the cultural exchange, which is wonderful, just to imagine what it's like to be essentially operationally an orphan. Most of the students in the class would have left Tibet, brought over by their relatives when they're very young, probably haven't have some distant relatives or maybe not any relatives in northern India. Can't contact their families because the Chinese have been jamming even cell phones lately. And so, that's an interesting and difficult life. And yet they're very happy with it. They're joyful when they need to be. It's not an easy life. I mean, there's illness, there's sickness, there's loneliness. So that was salutary in coming from, a pretty comfortable Western existence to see how they deal with their lives and are fine with their lives. And then the other counterpoint there was, which I guess I also mentioned a little bit, is, you know, the Western scientific tradition is very questing, is very ambitious, you know, Victorian agenda, that everything's got to get better, everything's got to get bigger, we got to learn more and more and approach total knowledge or whatever the final theories. And that's a very Western viewpoint, as you realize when you embed with a set of people thinking from an Eastern tradition. And so it makes you question all sorts of things, you know, that global sort of science ethos or agenda, the personal version of that involves ambition and publishing papers and reputation and academic status. You know, it makes you question all of those things. And so that's part of what I find when I go there. It hits both a small and a large reset button on all the things that I thought were important or the things I spend my time on. And hopefully, not always, of course, as soon as you get back into your real world, it just sort of ramps up again. Hopefully it lingers for longer, or hopefully there's a long-term part of my continuing association that affects the way I think about the minor frustrations of my life, my kind of angular colleagues in astronomy and in science and in the university and so on. I think it does, actually. It's given me a slightly different perspective.
Yeah. I mean, as far as how kind of humbly open to learning they are and how focused on the moment, at one point, I think in the book, you note that there are various ways to convey the scale of various things, number of stars, galaxies, whatever. And one way is to start saying, is to like count grains of sand. Mm-hmm. And you know, the number of grains of sand in this, and then such and such, I forget what, is like 1 billion times that or 50 times that. Mm-hmm. And, you know, these guys are like, sure, give us the sand. I mean, we'll actually count it, right? I mean,
well, and so the lesson I would take to my graduate students, say, you know, back into the science realm here, about how they do that, is that they are down with their data. I mean, they want to be in the world. They want to experience it. It's a nice empirical part of the Buddhist tradition, you know, going back to statements by the Buddha that, you know, you should be empirical, you should test ideas and hypothesis, you shouldn't take anything on authority, there's no dogma, there's no theology in that religion or philosophy. So they all follow that. And sometimes the students in the Western scientific tradition, you know, they're so teched up and they're so, you know, goal-oriented and so on, they forget that sort of base coat of paint that means that's how you get down with your data. I was struck out of my field by Barbara McClintock, was won Nobel Prize some decades ago for these elegant experiments on population genetics with corn. And when she was interviewed as part of winning Nobel Prize or just in general, she said some very striking things. A reporter, I think, just asked her, you know, how did you come up with these insights? You know, you're doing these very simple experiments with corn, and yet you've found profound things about genetics that way. And she said, well, I keep very careful journals, and I document everything, and I really live with my experiment. She said, in the end, I am the ear of corn. It's like, wow. And she's not a Buddhist or anything like that, but the reporter said, okay, I know what you mean. I know what you're saying. And my students, you know, need to be their ear of corn or their data from that quasar or that star. And sometimes that's a hard thing to do. And the monks, in their technically less sophisticated ways, are just going straight there. You know, they understand that to know science, to do science, to be hands-on, to fully incorporate it into your worldview, you have to just jump right in.
Mm-hmm. All right. Well, that's great. And really interesting book. Like I said, a lot of beautiful pictures. And a really interesting narrative about physics and philosophy and an encounter between two cultures. Humble before the void. Thanks a lot. Enjoy your subsequent trips to the Himalayas. I envy you.
Yeah. Thanks, Bob. I enjoyed this.
Me too. Okay. Take care.
Right.